Hello everyone, this is Yiqian Wang from Suzhou University. It is my great honor to present our work here, and the title is Subgrid Scale Modeling for Large Eddy Simulation based on Vortex Identification Methods. The core idea of this research is to introduce advanced Vortex identification methods into the construction of subgrid scale stress models for areas. Our objective is to more accurately capture and simulate the critical vortex structures and their energy transfer processes in turbulent flows. Here is the incompressible Navier-Stokes equation. And we all know that theoretically the NS equations are complete for any flow, whether laminar or turbulent. Only if the flow satisfies the underlying assumptions of continuum mechanics, incompressibility, and Newtonian fluid behavior. However, for turbulent flow, let's suppose the energy is injected into the flow at large eddies of length scale L0 and velocity scale U0. The rate of energy transfer scales with U0 square divided by tau 0, which is a characteristic time scale. And tau 0 equals U0 over L0 over U0. So the energy transfer scales with U0 to the third power over L0. Consistent with the energy cascade picture proposed by Richardson, the energy dissipation rate epsilon scales with U0 to the third power over L0. Thus, we have the relation that the energy containing length scale L0 scales with U0 to the third power over epsilon. According to the Kolmogorov hypothesis, energy is dissipated at the smallest eddies. The statistics of the smallest eddies are uniquely determined by nu, the viscosity, and epsilon. Using dimensional analysis, the Kolmogorov scale is defined as eta equals nu to the third power over epsilon and to the 1 over fourth power. Therefore, based on the two equations introduced, we have this relation L0 over eta scales with Reynolds number to the 3 over 4th power. So to resolve the smallest eddies and the energy containing eddies in a computation, the number of required computational grid points scales with Reynolds number to the 9 over 4th power. Therefore, for flows with Reynolds number equals 10 to the 7th power, the grid number required by a DNS would be 5.6 times 10 to the 15th power. That means DNS is still formidable for high Reynolds number engineering flows. To resolve the situation and to simulate turbulent flows, Reynolds averaged Navier-Stokes equation it was proposed. Rans decomposes the instantaneous flow variables into mean and fluctuating components. So UI equals UI bar plus UI prime. P equals P bar plus P prime. Applying this decomposition into the incompressible Navier-Stokes equation, introduced before yields this averaged Navier-Stokes equation. Because of the nonlinear term, the second term, the convection term, there is a unclosed term ui prime, and bar that need to be closed. We have to model this term by the mean quantities. So the RANS models are designed to provide mean flows, and nowadays RANS is still the industrial standard for engineering problems. However, RANS suffers from its inability to capture unsteady phenomena and significant deficiencies in predicting massively separated flows at all. The Reynolds average procedure inherently filters out vertical structures, consequently attempting to build turbulence models based on vortex identification methods within the RANS framework is fundamentally flawed. For instance, the mean flow field of a statistically stationary turbulent channel flow contains no resolved vortices by definition. Without these structures, the physical basis for modeling the Reynolds stresses through vortex dynamics is lost. The third methodology to simulate turbulence is large eddy simulation. On the other hand, LES filters the flow field, and the vortices would not be smeared completely. So UI now equals UI tilde plus UI prime, and P, the pressure, equals P tilde plus P prime. The common filters are box filters, Gaussian filters, and spectral cutoff filter. The filtered Navier-Stokes equation is given here, and again we have a unclosed term tau ij. So we have to introduce the so-called subgrid models to model this tau ij. The most famous subgrid model is Smagoriski model. It uses the turbulent viscosity hypothesis and relates the turbulent viscosity with the strain rate of the resolved flow. A particularly recognized problem of the Smagoriski model is its over-anticipation in a strong background shear, particularly a non-zero residual viscosity and shear stress at near the wall. We know that the problem can be mitigated by, for example, using the Van Driesch damping function or adopting the wall-adapting local eddy viscosity model. The dynamic Smagoriski model introduces a test filter with filter weights delta hat equals 2 delta. So we can get this Germano identity, and Lij equals T, capital Tij minus tau ij hat. Here Tij, capital Tij, is the SGS stress at the grid filter level, And the tau ij hat is a SGS model at the test filter level. In the dynamic Subgrid model, we model both stresses with Subgrid form and assume a same model constant. Of course, there is a hypothesis behind this that the cutoff scale is located in the inertial range. As the equations for the model constant is over-determined, and we generally use algorithm to compute the least square solution of the model constant. And generally, we need a homogeneous direction to average for stability. If we do not use the average, sometimes we will get like a negative viscosity, which will cause instability in the algorithm. So here is advantages and disadvantages of dynamic Subgrid model. So the advantages includes automatic coefficient determination. You don't have to man input the coefficient, and dynamic Subgrid model offers correct neural behavior. Its main limitations are it requires a homogeneous direction to do the average. And in addition, the test filter increases the computational cost. Another famous subgrid model is the wall adapting local eddy viscosity. Its purpose is to give proper neural scaling and no sensitivity to high shear and no dynamic procedure. So here are the equation are the WALE model, and C sub W is the constant, and the delta is the filter width. SIG is a filtered strain rate tensor, and SIGD is a traceless symmetric part of the square of the velocity gradient tensor. So it is quite complicated. So we first gave the statistics of turbulence of a turbulent channel at Rina tau equals 180. On the left is the velocity fluctuation components, u prime, and v prime, and w prime, and their averaged and squared statistics. And on the right, we have the statistics of Vortex vector. So as Vortex is a vector, it has three components. So we can also do this second order statistics. It should be mentioned we have used the full Vortex components, not the fluctuating part. So from the two figures, we can find similarities between the profiles, including the increase and decrease trend along the wall normal direction, and the ratio of the streamwise components to wall normal and spinewise components. On the other hand, we also presented the vorticity fluctuation components statistics and the S, which is used in the Subgrid model. We can see they are quite different from that of velocity fluctuations. So from these several pictures we can see that two advantages to develop tubular models based on the Vortex vector. First, in the laminar flow or laminar region of the turbulent flow, the Vortex-based model can automatically give zero eddy viscosity, thus avoiding the over-dissipation issue of a Subgrid model. Second, there is a high correlation between statistical information of Vortex and the velocity fluctuations. So we may expect to a better model. So we propose a Vortex-based Subgrid model, and it has a form similar to a Subgrid model. Nu t equals c sub v times delta to the second power times Vortex magnitude. And Cv is a model coefficient, and R is a filtered Vortex magnitude. Delta is again the filter width. We apply this model to decaying homogeneous isotropic turbulence, and to compare with the Comet-Bellet and Corson experiment of spatially decaying homogeneous turbulence. The computation solves the incompressible Navier-Stokes equation with a pseudo-spectral treatment, and 302/2 rule has been used to avoid aliasing error. The initial condition at T1 is constructed based on the energy spectrum, experimental energy spectrum. The mesh for LES includes 32 to the third power mass points, which leads to a cutoff wave number located in the inertial subrange. Shown in the figure is the energy spectrum. Another important issue to address is the determination of the model coefficient, CV and CS for the Subgrid models. We are comparing the Subgrid model and our new model. So here we use pilot simulations with dynamic Subgrid model and a similarly constructed dynamic Vortex-based Subgrid model. So by using this dynamics model, we determine the CV equals 0.038 and CS equals 0.03. Shown in the figure is the energy spectra obtained by the two Subgrid models. The symbols represent the experimental results, where colored lines are computational results. We can see that the two Subgrid model in the physical space, and the results of Subgrid model resembles the filtered energy spectra with the result. While the Vortex-based submodel matches the experimental spectra, which indicates that the Vortex-based model has properties resembles low-pass filter in the spectral space. It is thus demonstrated that for homogeneous isotropic turbulence, the new model is capable of modeling the influences of small scales to large scales and providing accurate spectra for wave numbers smaller than the cutoff wave number. The second case is turbulent channel flow at Reynolds tau equals 180. It can be seen that the Lutex-based subgrid model and the WARE model gives results resembles the DNS profile, while the no model case and the Subgrid model case significantly deviates from the DNS profile due to the lack of eddy viscosity. Note that the WARE model has a substantially different formulation than the Subgrid model, while we have used the same formulation for the Lutex-based subgrid model in both decaying homogeneous isotropic turbulence and turbulent channel flow. Time streamwise and span-wise averaged eddy viscosity for Subgrid model and WARE model and the Lutex-based model are given here. And we can see that the Subgrid model over-predicts the eddy viscosity near the wall surfaces, while WARE and the Lutex-based model predicts a small eddy viscosity near the wall, and the eddy viscosity increases with the distance to the wall, saturate around y over h equals 0.5. The eddy viscosity behavior of Lutex-based model is basically in accordance with our physical understanding. While a detailed comparison between WLE and the Lutex-based model in the right figure reveals that the eddy viscosity on the wall surface predicted by the Lutex model strictly equal to 0, while the WARE model, the eddy viscosity is small but not 0. We have to say that according to the no-slip condition imposed on the wall surfaces, there should be no velocity fluctuations on the wall, and the predicted eddy viscosity should also be there. Using the two cases, we have shown that introducing vortex identification methods into the subgrid model gives better results. So now we want to compare different vortex identification methods, including Q, lambda2, delta, lambda ci, and the Lutex vector. So by doing the dimensional analysis and some cutoff of the vortex identification parameters, we construct this nu t equals cs delta to delta square psi vortex-based subgrid models, and we compare them in turbulent channel flow, and we can see that they all exhibit a good behavior, and the best line should from the figure on the right, the best line should be the Lutex and like lambda ci. Here is a model coefficient by the dynamic version of the vortex-based subgrid models, and the model coefficient predicted by the dynamic procedure shows that the Lutex coefficient is almost the same no matter near the wall or away from the wall, and its variation coefficient is the smallest of all the models. And here is the parameters, the model coefficient determined by the previous dynamic models. So that's all. We have introduced the uh, vertex vertex identification methods, especially the Lutex vector, into subgrid models, and we found that the results is good, is very good, and we are looking forward to do more numerical tests on new cases. Thank you.